In the unit 1, we have talked about the hardness and the degree of the hardness, how we can express the hardness in CaCO3 equivalent. Now we will see how we can analyze the hardness in the lab, and the method which is used to analyze the hardness in the water sample is called EDTA method. In this lecture, we are going to learn the EDTA method. What's the principle of the method? The theory and the reactions involved in the method. What is the procedure of the method? The learning outcome of this lecture will be the students will able to understand about this method of the estimation of the hardness, that is EDTA method. What is its principle, theory, reactions and procedure. So let's start the estimation of the hardness by this EDTA method. The EDTA method is also called the complexometric titration. Means it is a type of volumetric analysis. Why it is called complexometric titration? Because EDTA act as a ligand which form the stable complex with the hardness causing ions, calcium, magnesium as well as other heavy metal ions, and that's why it is called the complexometric titration. So the principle involved in this method, we can easily understand that EDTA is a hexadentate ligand. Hexadentate means having 6 donating sites. From the 6th site, it can donate the electron. Depending on the donating sites where the ligand can give the electron, the ligand can be classified into various types: unidentate, bidentate, tridentate, and after 3 we can easily say polydentate. So it comes in the category of the polydentate ligand, having 6 donating sites which form the stable complex with the hardness causing metal ions, calcium, magnesium, as well as other heavy metal ions. So the main principle here, forming the complex, stable complex. On the basis of that, we can estimate the hardness of our water sample. Now we see, as we are seeing, the EDTA is one of the most important requirement for the estimation of the hardness. Some other chemicals are also required. The standard solution of EDTA, we take m by 100 EDTA. It's a molar solution, and we have the hard water sample. Now it's a titration, so indicator is required. Which indicator we use? EBT, that is aerochrome black tea. And one most important reagent here required, that is basic buffer solution. Without that, this method cannot be done. Now we see the theory of the EDTA method and each one of the reagent playing the role in the method. So it comes out in the theory and then we see the reactions. So what is the full form of EDTA? It is ethylene diamine tetraacetic acid, which is having 4 protons in the form of acid, that is tetraprotic acid. So this is the structure of the EDTA, pure EDTA, having ethylene, this CH2 single CH2, diamine, 2 nitrogen here, and tetraacetic acid. We have CH2 COOH. This is 4 CH2COOH is 4 tetraacetic acid. So having these two protons and these two protons. So it is a tetraprotic acid. So having 6 donating sites, you can able to see these proton when dissolved in the water. The protons separated. So 1, 2, 3, 4. 4 protons separated, 4 sites develop for the electron donor and the 2 lone pair of the electron on the nitrogen. So the complete 6 donating sites it is having the hexadentate ligand. So as we have seen the pure EDTA structure, the pure EDTA can be easily represented as H4Y, having 4 protons as we have seen in the structure, and rest of the functional group can be represented by the Y. Because of its limited solubility, means it is less soluble in the water. This is the main limitation. So it is not used directly in the estimation of the hardness. Generally, we use disodium salt of EDTA. That is used for the estimation of the hardness, which can be represented as disodium salt having 2 sodium, 2 protons, and rest of the group can be represented as Y. So the structure of the disodium salt of EDTA is this, having 2 protons are replaced by 2 sodium and the rest of the 2 protons remain the same. So this is the disodium salt. This is sodium. Disodium salt of EDTA. This is used because it is highly soluble in water and it forms the complex with the hardness causing ion. So if we see when it dissolves in the water, the sodium ions can be easily released and it forms the ionic species H2Y2 negative. So it is seen that 1 mole of the complex forming ion, that is H2Y2 negative, reacts with the 1 mole of the hardness causing metal ion, and when it goes for reacting, the 2 moles of the H ion released. So when the formation of H ion produces, it decreases the pH of the solution. So when it decreases the pH of the solution, the reverse reaction can take place. That is why, or this is the reason, the metal EDTA titration are carried out at a maintained pH or a fixed pH, that is 8 to 10 or nearby 10. So this is the pH which is having nearby 10, that comes in the neutral or alkaline solution, and the best pH is to be maintained in such kind of the titration is 8 to 10 or nearby 10. So here it is specifically written this pH is maintained in this method. So the metal ion here M2 plus is representing the hardness causing ion. When react with the EDTA species, 2 H ion released and it form the colorless stable complex with the metal ion. This is stable complex EDTA is forming and it is colorless. So if your divalent cation like calcium and magnesium when react with EDTA, it form the colorless stable complex. Likewise, having the trivalent ion, it also form the stable complex with the charge 1. And if it is tetravalent cations, it also form the complex with the EDTA. the same reaction is taking up. So this reaction should be occurred at the pH nearby 10. We have seen previously, this is written that this reaction to be take place at the maintained pH, otherwise the again the complex break into the ionic species. That is the meaning here. That's why we have to maintain the pH, and for this method it is very essential to maintain the pH of the solution. Now the next role comes up of EBT. What is EBT? EBT is an indicator. What is its name? Eriochrome black tea indicator. It is a metal ion indicator. Let's see its structure. The structure is having two naphthenic group. Here you are able to see two benzene ring, that is called naphthenic. Here the another two benzene ring having the naphthenic group. Two phenolic group, OH. One is this and the another one is this. So it is also acidic in nature, having the N double bond N, that is azo group, nitro group and sulfonic group with the sodium. So it is the black in color. Black tea indicator, it is Eriochrome black tea indicator, that is black in color. But when it dissolved in the water, it forms various ionic species which have the different color. If we see its chemical name, that is sodium 1, 1-hydroxy, 2-naphthylazo, 6-nitro, 2-naphthol, 4-sulfonate. So initially when it dissolved in the water, the sodium releases and the first ionic species which we get, that is H2 ion negative, which is red in color. So let's see the various species. This is the representation of EBT. We are representing, so one is in the structure, one sodium is having two phenolic group proton and rest of the part is indicating by ion. So it is initially the black in color. When it dissolves in the water, the sodium releases and we have the ionic species H2 ion negative, that is red in color. So initially the sodium first release and it having one negative charge, it is red in color, and then one proton removes, the charge comes to negative and which is blue in color. Then one more proton is removed. Finally, we have the 3 negative charge and the color of this species is yellowish orange. So all the ionic species of EBT is pH dependent. You are able to see that in alkaline range, that is 11.5 above, we are having higher alkaline range, we have yellowish orange. In between 6.3 and 11.5 we have the blue form of EBT, and below 6.3 in the acidic medium we have the ionic species red. So as we are maintaining the pH in the titration, that is 8 to 10 or nearby 10, which EBT form dominates? Blue form, because we are maintaining the 10 pH, the blue form of EBT participate. So blue form of indicator gives the wine red complex with the hardness causing ion. Wine red complex is the unstable complex. If the hardness is present and this is the EBT blue form, reacts to form this wine red color unstable complex. This is not stable complex as EDTA. So wine red color we go for appearing, it is because of the formation of unstable complex with the indicator. So the pH of 10, it is very satisfactory in this titration. And if we are for this indicator also, the pH 10 is most satisfactory. At a high pH value, the magnesium ion may be precipitate out as the magnesium hydroxide, and also the blue form is partially converted into the 3 negative species ion, which is the yellowish orange. If it is changes to the yellowish orange species, it do not form the complex. So at lower pH value, the magnesium and the indicator are very loosely bonded to maintain the red color. So at the low pH value, the red color complex cannot be formed exactly because it is loosely bonded. And at the high pH value, it can be converted into the yellowish orange species which do not form the complex. So in strongly acidic solutions, indicator tend to polymerize to red brown. So the most satisfactory pH for the indicator also, that is 10, because at this pH the blue form the complex with the hardness causing ion unstable complex, that is of wine red color. Now the third important role comes in the method, that is buffer solution. So as we are able to see that a EDTA reaction should occur on the constant pH, and pH should be maintained, and indicator also at a pH 10, it playing the role. So the buffer solution plays an important role of maintaining the pH. How you go for maintaining the pH so that your reaction proceeds. So here, which type of the buffer solution? Buffer solutions are of two types, acidic buffer and basic buffer. When we are to maintain the acidic pH, that is below 7, we go for using acidic buffer. And if we want to maintain the pH in the alkaline medium, the basic range, we should use the basic buffer. As we have to maintain the pH, that is 10, so for that we have to use the basic buffer solution. So basic buffer solution of ammonium chloride and ammonium hydroxide is used for the pH 10. So the last reaction, if we see that the wine red unstable color complex is formed when we add the indicator in the hard water, and this unstable complex when we go for titrating with the EDTA. So what happened? This is the unstable complex. So it can be easily displaced. So EDTA goes on displacing this unstable complex and form the stable complex with the hardness causing ion. Understood? So here the magnesium is the hardness causing ion. Suppose magnesium is there, and the EBT is formed the wide red complex with the magnesium, and when it is going with the titration with the EDTA, so the EDTA replaces this indicator and form the complex magnesium stable complex with EDTA, which is colorless. And as soon as this complex is formed, your indicator become free, and when your indicator become free, we have which color we can able to see, because at the pH 10 its color is blue. So that is the blue form which become free here. So the end point comes the wine red to blue. As soon as your solution changes the color from wine red to the blue, you have the indication that your complex is formed and you have to stop the titration. That's the main thing. So when we see all the role of the reagents and the reactions involved in the method, so we can apply with the three simple steps. We take the standard EDTA solution in a common equipment of the volumetric analysis, that is burette, and in the conical flask we take 10 ml of the hard water sample. So when we are taking the hard water sample, when we go for adding firstly the buffer solution in it to maintain the pH, how much pH we have to maintain? We have to maintain nearby 10. So as soon as you just go for adding the buffer solution and then you add the indicator, you get the wine red color. And wine red, if you are not getting, means your water is not hard. So wine red color, when you get, you have to go with the titration. Wine red color is due to the formation of the unstable complex of the indicator to the metal ions, and then we titrate with the EDTA, and finally we have a stable complex. Blue color is of what? The blue color is of the free indicator color. It is not, because the EDTA metal ion complex is colorless, and that becomes our endpoint. So this is a very simple method for the estimation of the hardness, because it is simple to calculate all type of the hardness, and it gives accurate and the reliable results for the hardness of the water sample. Thank you and take care.